Welcome back, my mathematical minions and minionettes. Well, as we start on CT2, and by the way, you may want to turn around and put that, this is CT2, congruent triangles 2. We're going to talk about bisectors of a triangle. Now, we've already talked about bisectors a little bit, but we're going to get into this a little bit more with the construction. So remember, bi means two, sect means to cut. So bisectors are things that cut it in two. So up to this point, we've talked about two different types of bisectors. First of all, we had some segment bisectors. So segment bisectors. So if we look at this one, if we look at segment AB here, if we bisect it, that means that point P here is the midpoint, okay? So let's give it another point here. So in other words, that means that PQ is a bisector. So PQ, and that's a line PQ, is a bisector of segment AB. So PQ is a bisector. Why? Because it's the midpoint. It cuts it in half. You see the congruent marks. This one congruent to this mark. So those segments, this congruent mark tells us that this segment is congruent to this segment. So that's why the congruent marks. Now, the next one is a perpendicular bisector. So if we look at this one, let's go with J. This is point R. This is point K. And we need another point. Let's call it S right here. Okay, so we had a perpendicular bisector. Now remember, perpendicular bisectors, if that were the case, if we're looking at RS here, if line RS is a perpendicular, remember that's a symbol for perpendicular, bisector of JK. If that's the case, then that tells us that not only is this segment congruent to this segment, well, get my pen to work, there we go, but it also forms a right angle. So that's a perpendicular bisector. So difference between the two. So let's jump in here and let's take a look at the perpendicular bisector theorem. We're going to need to know this, so make sure you get this copied down. So go ahead and hit pause, copy it down in your notebook. Okay, so perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segments. So since CD here, if CD is a perpendicular bisector, so if we say that CD is perpendicular bisector, then that means any point that's on CD is going to be equidistant to A and B. So that means that if CD is a perpendicular bisector, then that means that AC here, that AC has to be congruent to, equal in length to CB. That means that if we had some other point, and we'll call this one right here R, then that means that AR is congruent to BR. So AR is congruent to BR. So any point that lies on that perpendicular bisector would be congruent. So if we had some other point down here, we got this point down here, and we call this point Y, well, guess what? AY would be congruent to BY. So that's what the perpendicular bisector theorem says. Now, we also have a converse of that. Converse, okay? Remember converse, you should have that in your notes already. So, and it says if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector. So that tells us that if we have some line, if the distance between a point on the line is equidistant to each of the two endpoints of this triangle or of this segment here, then that means that it's on the perpendicular bisector, that this segment, or this line right here, this line has to be a perpendicular bisector. If points that I pick on this are equidistant to the endpoint, this is congruent to this is congruent to this, then this line has to be a perpendicular bisector. That's what the converse of the perpendicular bisector theorem comes into. So that's going to come in when we're dealing with some lines there. When we can prove that it's equidistant to the endpoint, that lets us say that it must be perpendicular. It has to be a perpendicular bisector. That lets us come in and say things like, hey, this has to be a right angle, okay? We can say that by the converse of the perpendicular bisector theorem. We can also say things like, hey, the distance from A to D has to be the same as the distance from D to B. Okay? Why? Because of the converse of the perpendicular bisector theorem. So that's where this one comes into play. Let's just do a little bit different than the perpendicular bisector. Perpendicular bisector says, hey, if we can prove we have a right angle, and we can prove that not only is this line perpendicular, but it intersects at the midpoint of this segment, then that lets us say, hey, any point we pick on here is going to be equidistant. Or let's just start dealing with isosceles triangles. Okay? So let's look at some examples of these and see how this comes into play. So finding this one. So notice what we've got. We've got CA here forms a right angle, and that C to B and C to D are congruent to each other. Okay, so we see that. We've got CB is congruent to CD. We've got that BD is perpendicular to AC. Okay, we can see that. That means that this has to be a perpendicular bisector. That means that the distance from any point that's on this line has to be equidistant to each of these two endpoints. So take a look. If AD is 4.1, then AB has to be, you got it, 4.1. Okay, so AB equals 4.1. There's our distance right there. All right, so let's look at, and that's by the perpendicular bisector theorem. So look at WY. Okay, notice here, we're turning around, we're looking at this one. So in the case of WY right here, since we've got that, by the way, this is a 3, not some weird. Since we know that, one, we have a right angle, and these distances are the same, that means that this must be a perpendicular bisector. That means that the distance from, that this has to be a midpoint, so this distance has to be 3. So WY has to equal 3. So there's some examples of using the perpendicular bisector theorem. All right, so let's look at some more definitions now. The circumcenter theorem. Circumcenter. Okay, be careful with that one. Circumcenter. It says the perpendicular bisectors of a triangle intersect at a point called the circumcenter that is equidistant from the vertices of the triangle. So that says if we have a triangle, if we draw the perpendicular bisectors, how many perpendicular bisectors would there be for a triangle? Correct, 3, because there's 3 midpoints from each side. So notice here is a perpendicular bisector. Midpoint here, this is a perpendicular bisector. Okay? Midpoint here, so this is a perpendicular bisector. They all 3 intersect at a point, and that point, this point that they intersect, is called the circumcenter. Make sure you have that. Okay? That will be an important one that we're looking at. So the circumcenter, that's this point right here. And it is equidistant from the vertices. So that says that the distance from the circumcenter to each vertex, that this distance, right here, let's see, that distance has to be the same as this distance, has to be the same as this distance. Well, I guess I've already got single congruent marks. These are going to be 4. 4, 2, 3, 4, 2, 3, 4. Okay, so each of those are equidistant from the vertices, so that's a circumcenter. Now, a couple of definitions we need to know. Add these in. These will be important as we're going along. Locus, set of points that satisfies a particular condition. So that would be the perpendicular bisector is a locus of all points equidistant from the endpoints of a segment. So the locus is just points that satisfies a certain condition, whatever it is. So we were talking about, if we were asking you to find the locus of all, the locus of the perpendicular bisector, then that's any point that's equidistant from the endpoint. Okay, so the next one, concurrent. Concurrent, okay? When 3 or more lines intersect at a common point. So we look here, because we have 3 perpendicular bisectors intersect here, okay, because they do, that this point that we know as a circumcenter is called a point of concurrency. So if it were to 3 other things, say 3 medians that intersect, they intersect at a point of concurrency. Now it's going to have a special name. Like this one, the 3 perpendicular bisectors are called circumcenter. The others may have a different name, but we say that that place where 3 or more lines intersect is called the point of concurrency. All right, and the last one, circumcenter. Circumcenter, which is what we have here. It's the point of concurrency of the perpendicular bisector. So adding those terms. Now, Now that we've talked about segment bisectors, let's look at angle bisector theorem. Okay, so angle bisector theorem. It says if a point is on the angle bisector of an angle, remember a bisector, angle bisector, cuts an angle in half. So that means that if this is an angle bisector, okay, if this is an angle bisector, then it cuts the angle in half. Notice the congruent marks, this angle congruent to this angle. That means that we're dealing with an angle bisector. Then, if a point is on the angle bisector, any point that we pick that's on here, this point here we've got, this point here, this point here, then it is equidistant from the sides of the angle. So remember, an angle is made up of two rays, so the distance from here, this distance, is the same as this distance. That's why we have these congruent marks here. If we picked this point right here, if we drew a perpendicular, and we drew a perpendicular here, okay, those two would be the exact same length. Okay, so that's the angle bisector theorem. Now, the converse of the angle bisector theorem says that if we have a point that is inside an angle that is equidistant, so the converse says if a point is in the interior of an angle, so it's inside of an angle, and it is equidistant from the side, so we look at this one, and the distance from here to this side is the same as the distance from to this side. If those two are true, then that means that this point has to be on the perpendicular bisector, the angle bisector, sorry. It has to be on the angle bisector. So if we can find any point, some point is in here in the middle, okay, and it's equidistant from the two sides of the angle, then it must be on the angle bisector. So let's look at some examples of this and see what we can do with this. So in this case up here, notice what we've got. We've got these two angles are congruent. That means that this segment XZ, or ray ZX here, look at ray ZX, must be an angle bisector. Angle bisector. It has to be. How do we know that? Well, because it cuts this angle into two congruent parts. So if it's on that angle bisector, then we know that the distance from any point on this line to each side has to be the same. So if this is 7, if this up here is 7 right here, then XY has to be 7. XY has to equal 7. All right? Now, flip side, so that's the angle bisector theorem. Look at the converse in this one here. Okay? So in this case, we've got two angles here, the angles that are congruent. That means that this JS right here has to be an angle bisector. That means that this distance from M to S and from P to S has to be the same. So what do we do here? We set up and say, hey, then 3x plus 5 has to equal 6x minus 7. We go ahead and solve it. Subtract 3x from both sides. Cancels out. Adding 7 to both sides. Cancels out. And we get 12 equals 3x. So x has to equal 4. So x is 4. So how far is it from S to P? Well, that's 6 times 4 minus 7. 24 minus 7, so it would have to be 17. So with the other one. So there's using that angle bisector theorem and the converse of the angle bisector theorem. Using those right there. Okay, so same idea as we had before. You know, we had a circumcenter before. Now we have an incenter. It says the angle bisectors of a triangle intersect at a point called the incenter. Because there's 3 angle bisectors, that means that this is a point of concurrency. This is a point of concurrency, and we call this point of concurrency, the point of concurrency for angle bisectors is called the incenter. The point of concurrency for perpendicular bisectors is called a circumcenter. I know they sound alike, but you're going to have to keep them straight. The perpendicular or the angle bisectors, the point of concurrency is called the incenter, and it is equidistant from the sides of a triangle. Remember, circumcenter is equidistant from the vertices of the triangle, from the end points of the triangle. And incenter is equidistant from the sides of a triangle. So as we add this one, circumcenter, the point of concurrency of the angle bisectors. All right? So kind of wraps it up. Make sure we can keep those straight. We looked at angle bisectors and perpendicular bisectors, added circumcenter and incenter. We're going to have a running list here. We've got some others we have to talk about. We still have to talk about medians. We still have to talk about altitudes for a triangle. So some others we're going to add, but this is a good place. All right, so I will see you in class tomorrow. Enjoy your evening.